Okay, if you're just joining us in this video, we're in the middle of problem 17. I'm working out homework problems from section 4.6, optimization. I've done two previous problems. I believe I worked on problem 11 and problem 5 on the previous video on 4.6. Halfway through solving problem 17, the camera flipped horizontally and the problem was presented backwards on the whiteboard. So I stopped that video and restarted this video, picking up where we left off with problem 17. So we had drawn our picture in problem 17. We've got our sketch drawn. Everything's labeled here. I've identified while you were gone that this is a 30, 60, 90 triangle. I had done that in the previous video, but now I've labeled the 30 degree and the 60 degree angle for us. We are asked to maximize the area of the rectangle. So we need a formula for the area of a rectangle. And so the area here is 2x times y. Why is it 2x times y? Well, if we take a look at our rectangle is x by x, right? Each half here is x. So that side is 2x. The height, this is the point xy right here. So the height is y. So we have an area of 2xy. Once again, we've reached that point that we reach on optimization problems where we have an equation in two variables and we need to reduce it to one. What are we going to do to reduce this to one variable? Well, we're going to take a look at our sketch and we're going to try to come up with some way of rewriting this to eliminate either x or y. I've labeled all the pertinent pieces. For example, we know this leg is y. We know this leg. Let's start with, we know this side of the triangle from here to here is L, so half of it is L over 2. That piece is x. The entire thing is L over 2, which means that this piece right here then is the entire piece, L over 2, minus the part we've used, L over 2 minus x. Now from here, we're going to have to use some trigonometry, right? We've got a 30, 60, 90 triangle. We have two legs of a 30, 60, 90 triangle. So what can we utilize to try to express either x or y in terms of the other variable? Well, we can use tangent, right? This is 30 degrees right here. Tangent is opposite over adjacent. We can say that tangent of 30 degrees is equal to the opposite side, which is L over 2 minus x, divided by the adjacent side, which is y. Now, we know what tangent of 30 degrees is, right? If we just quickly draw a triangle up here, we have 1, 2, square root of 3. Tangent of 30 degrees is 1 over root 3. So what do we have here? We have 1 over the square root of 3 is equal to L over 2 minus x, all divided by y. If we rewrite this, right, we can multiply both sides by y. We get y over the square root of 3 is equal to, right, the y comes up here, L over 2 minus x. And now if we simplify that, we get y equals root 3 times L over 2 minus x. And there we go. We have rewritten y in terms of x using our 30, 60, 90 triangle. Now, where does that lead us? Well, it leads us to an expression, right? To an expression for a that now has only one variable. A is equal to 2x times y, but we now know y is the square root of 3 times L over 2 minus x. So if we multiply that together, what do we get? We get 2 root 3. This is going to be xl, right? 2 root 3. Put those out in front. We're going to get lx over 2 minus x squared. Right? So let's just take another look at that and make sure we multiplied that correctly. I put the root 3 out here with the 2, the constants out in front. X times L over 2 is Lx over 2. X times negative x is minus x squared. So this is our expression for area. Now what are we going to do with that? We're going to take the derivative. Right? We're going to to find the derivative. A prime. Now we have a constant, so that's 2 root 3. This, when I take the derivative of x times L over 2, that just gives me L over 2. And when I take the derivative of negative x squared, I get minus 2x. Right? Now what are we going to do from here? Well, we're going to do what we always do. We're going to take the derivative and we're going to set it equal to 0. Again, it's a polynomial, so I'm going to skip this time the step where we set the derivative and ask ourselves, when does it fail to exist? When is this going to equal 0? Well, it's going to equal 0. 2 root 3 is not 0. So it's going to equal 0 when L over 2 minus 2x equals 0. Now remember, L is a constant. It's not a variable. So this says, right, this says L over 2 equals 2x, or it tells us that L over 4 equals x. Now, the problem asks for the dimensions of the rectangle. Find the dimensions of the rectangle that maximizes the area. We have found one of the dimensions. If we go back to our picture up here, the width of our rectangle, right? The width of our rectangle is 2x. We have that right here. So this is the actual width of our rectangle. Right? That's the width of our rectangle, 2x. 2x is the width, so the width of our rectangle is L over 2. Now we're left with to find the height. What do we have to do? We got to find the height, right? That's what we have to do next. So how are we going to find the height? Well, we have an expression right here for the height, right? This is the height right here. We can find the height by substituting in x. We know x is L over 4. So what do we get for our height? We get y equals the square root of 3 times L over 2 minus L over 4. Well, if we rewrite that, right, if we just rewrite that and think about it logically, this is a half of an L minus a fourth of an L. And we all know if we have half of something minus a fourth, that gives us a half. So we're left here with y equals, right? Y equals the square root of 3 times L over 4. Or root 3L over 4. That's our height. Now, they didn't ask us to find the area of the rectangle in the problem. We could at this point. We have the height, we have the width. We could easily find the area. But they just asked us for the dimensions. So the dimensions of our rectangle are L over 2 by, right, our width, by our height, square root of 3 times L over 4. Those are our dimensions of our rectangle. All right, so that finally gets us the answer of problem 17. Let me go ahead and clean this. Now, the rest of the homework problems are very similar to these problems. I'll go ahead and do one more, right? One more. I'll work on problem 21. It's very similar to problem 17 in the sense that it has a shape inscribed in a different shape. So those problems tend to drive students a little crazy. So we'll work on one more of those. So let's take a look at question 21. All right. 21 says, find the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius r. All right. So we want to maximize the area of an isosceles triangle. And we're going to inscribe it. What we're given, right, our given is that we have a circle of radius r. All right? So where do we begin? Well, we begin with a picture. Right? We begin with a picture. So we're going to start with our circle. Right? Here's our circle. And what do we know about our circle? Well, we know its radius is r. So we're going to begin by adding a coordinate system here to our circle. Right? We're going to add this. Now, what do we want to do here? We want to inscribe an isosceles triangle in this circle. So if we have a circle, the radius is r, right? And we put an isosceles triangle in here. An isosceles triangle. So what is an isosceles triangle? Well, an isosceles triangle means that this side and this side are congruent, right? Those sides are congruent. Okay, that was frightening. You might have noticed that while you were gone, the diagram changed a bit. I actually paused the video and erased my other diagram. It was sloppy. It was embarrassing. So we left off, right? We left off with the triangle drawn inside of the green circle. Now we're back with the triangle drawn inside of the blue circle. At least the diagram is less embarrassing now, right? So what do we know? What are we told here? Remember, we're told that the radius of our circle is r, right? The radius equals r. So how are we going to maximize the area of our triangle? Well, we're going to remember that the area of a triangle, right, is 1/2 base times height. Well, that's not an h. 1/2 base times height. So if we take a look at our triangle, I'm going to label this point right here, xy. I'm going to call this side x, this distance here x. I'm going to call this distance right here y. Okay? Now, why did I pick those? I picked those because I know this distance from here to here, this is r, and I also know that this is r, right? That's the radius of one of the circle. That's why I picked this point, so I could draw this radius right here and get a right triangle. Why do I need a right triangle? Well, because if we transform our equation over here into the variables that we have over here, what do we know right now? What's the area of our triangle, right? Our triangle has a half, right? That's the formula. The base of our triangle, if we look at the base of our triangle, this is x, this is also x. So the base of our triangle is 2x. And now, what's the height of our triangle? Well, the height goes from here to here. This piece is r, this piece is y, so the height is y plus r. Now, if we simplify that, that's x times y plus r. Once again, we've reached that point in every optimization problem it seems to happen where we have an equation for the quantity that we want to, in this case, maximize. We want to maximize the area, but it's written in terms of two variables. Now, how can we eliminate one of these variables? Well, we can come over here and we can take a look at our picture. We have a right triangle right here. This is a right triangle. And because it's a right triangle, we know that x squared, one leg squared, plus y squared, the other leg squared, equals the hypotenuse squared. Now that tells us then that x squared, right, is equal to r squared minus y squared. We would like to get rid of one of these two variables. I'm going to eliminate the x. I don't want to eliminate the y. The y is inside of this quantity plus r. I'm going to eliminate the x. It stands alone. So we get x equals the square root of r squared minus y squared, right? R squared minus y squared. So we can rewrite our equation over here as area equals x, which is the square root of r squared minus y squared times y plus r. Now what are we going to do? We're going to find the derivative. So we're going to have to use the product rule, right? The derivative of this is going to be 1/2 r squared minus y squared to the minus 1/2 times the derivative of what's inside. R is a constant, so r squared is a constant, so the derivative of what's inside is negative 2y, right? Now that's going to be multiplied by y plus r. Plus the first term, the square root of r squared minus y squared, times the derivative of y plus r. Again, r is a constant. This is just y, so the derivative of y is 1. Now what do we have? If we simplify this 2 cancels this 1/2. This goes in the denominator, so down below we have the square root of r squared minus y squared. The numerator now is y times y plus r. So we have minus, from here, y squared plus yr. Okay. And then what do we have over here? We have plus, and we have the square root of r squared minus y squared. Now we want to set this equal to 0. What does that mean? Well, that means this is going to be equal to 0, right? I'm going to save myself a little time here, which means this piece can move over here, can't it? So we would have minus y squared plus yr over the square root of r squared minus y squared equals minus the square root of r squared minus y squared. Once we move that over, it becomes a negative. Those cancel. We can multiply up here, and we have y squared plus yr equals, this radical times this radical makes that just r squared minus y squared. Now, if we bring those terms over here, what are we left with? We're left with 2y squared, right, plus yr minus r squared equals 0. Now, if we factor this, right, what are we going to get? We're going to get 2y and a y. And then we need a minus r squared. So we're going to need an r here and an r here. We need a plus yr. So this term times this term is going to be plus 2yr. This times this is going to be 1yr. We want a positive left, so this is going to be plus, and this is going to be minus. Remember, that equals 0. So now we have 2y minus r equals 0, or y equals negative r. Right? I skipped a step there. That would be, I'm sorry, here, I'll go ahead and put that step back in. That would be y plus r equals 0. So we would get y equals negative r. Now that makes no sense. This y value right here can't be a negative the radius. The radius is a positive number, so minus r is a negative number. So this gets eliminated. So what do we get from here? We get 2y equals r, or y equals r over 2. Now, they asked us, right, in problem 21, they said find the dimensions of the of the isosceles triangle. They want the dimensions of the isosceles triangle of largest area, all right? Well, right now, we know the height of this triangle is r plus y. This is y, so our height, right, our height is r plus y, which is r plus r over 2, or 3r over 2. And we know what the base is, right? We know what the base is. The base of this rectangle is 2x, right? So the base, based on our picture, is 2x. And we know what x is. We can go all the way back. Oh, here it is right here. To here. And we can say, okay, what does 1x equal? X equals the square root of r squared minus y squared. If we square y, we get r squared over 4. Well, we have 1r squared minus a fourth of an r squared, don't we? Isn't this really just this? It's just 1r squared minus 1/4 of an r squared. Well, that gets us the square root of 3/4 r squared, which simplifies. Square root of 4 is 2, the square root of r is r. Sorry, the square root of r squared is r. And then we get square root of 3 all over 2. Now that's x. Our base, however, is 2x, so our base is 2 times the square root of 3r over 2, or our base is root 3r. All right? Wow, that was a lot of fun, he says sarcastically. All right, so that's going to conclude my homework solution video on section 4.6, optimization problems. I did 4 of the problems for you, so hopefully that gets you going and allows you to make some progress with your homework. I hope everybody has a wonderful day.